Okay, so in this video, I will walk you through the Python script that's associated with um, a PBR with heat effects problem. So we're looking at energy balances in tubular reactors. And after deriving all the balances, there's an example problem here. The elementary gas phase reaction A plus B goes back and forth to 2C is carried out in a PBR with pressure drop. So we want to plot X, the conversion, XE, the equilibrium conversion, T, the reactor temperature, TA, the coolant temperature, and the reaction rate, RA, all as a function of catalyst weight for 4 different cases: 1, adiabatic; 2, co-current heat exchange; 3, countercurrent heat exchange; and 4, constant coolant temperature. And we're given this data. So we're going to solve that in Python. So one of the things that I like to do before I start out a Python solution is to make sure that I'm working in consistent units. So I'm looking at moles, so gram moles. Time unit is going to be seconds. My volume unit, so this is molarity, so that means that the denominator in that unit is going to be either liters or cubic decimeters. Temperature, Kelvin. I always need to be working in absolute temperature, but of course the other option is Rankine. Here I'm going to work in Kelvin. Energy units is going to be either calories or kilocalories. So I have calories here and kilocalories here. What I'm going to do is I'm just going to immediately convert all of these into kilocalories. I just like to work with kilocalories a little bit more than calories. So when I enter in my heat capacities into Python, they're all going to be divided by 1,000. What else? So catalyst weight is in kilograms. So we know that by the rate constant and then also the pressure drop parameter. This UA term, so I want to convert this calories to kilocalories, so I do that by dividing by 1,000. Also, this meters cubed, I want this is in meters cubed, but all of my other volume units are in liters. So to do that, I would divide by 1,000 again, so that I would be in kilocalories per second per liter per Kelvin. And then again here for this catalyst, this is the density of catalyst, so 1,400 kilograms per meter cubed. I'm going to divide that by 1,000, which puts me at 1.4 kilograms per liter. So I'm going to do all of those. I'm going to analyze my units, and then I'm going to make all of those units conversions before I go to Python. So now let's go to Python. So first thing I want to do, I'm going to initialize the different math functions that I'm going to use. So a couple here that I've added, this math, this is going to be what allows me to do exponentials. I'm going to have to do exponentials both to for the Arrhenius equation to convert my rate constant from the reference temperature to the actual temperature, and also my equilibrium constant from the reference temperature to the reaction temperature. And to do that, I need this math library, and I'll show you that in just a second. The rest of these we've all used before, but one thing is that normally we're looking at solving ODEs or systems of algebraic equations. In this case, I'm going to use both of those, and I'll show you why, so I've included both of those here. Entering all my constants here. So again, I've already converted these into a consistent set of units. So for example, the heat capacities are now in kilocalories per mole, whereas they were given, or kilocalories per mole Kelvin, where they were given in calories per mole Kelvin. And then additionally, the heat transfer coefficient, divided that by a total factor of 1 million in order to get it into units of kilocalories per second per liter per Kelvin. And then also this rho B here, I've already divided that out. Gas constant, I looked that up. I want the value that's in kilocalories per mole Kelvin because that's what's consistent with all of the other units here. Another thing that I'm going to do in here, so I'm looking at these 4 cases. I'm going to integrate this system of ODEs 4 different times, 1 for each case. When I do that, I'm going to integrate over the same catalyst weight. So normally I specify this in my different solutions. I'm just going to specify it up front up here so that I only have to do that once. Not necessary to do, but that's what I've done here. Okay, so now I can go into my different cases. This is my constant TA case, so I have a cooling fluid, and the cooling fluid is constant in temperature at every point along the reactor. So to do this, I'm going to set up my different balances. I have 3 different variables now that I'm worrying about. One is conversion, so that's going to be my mole balance. One is my pressure, so that's going to be my Ergun equation. And then one is the temperature of my reactor fluid. That's going to be my energy balance. I also have this temperature of the reactor fluid, but that's constant, so I'm just going to set it up there. One key thing to note, so when I set up my concentration equations, the nice thing about this reaction, epsilon is equal to 0, so I don't have a change in volumetric flow rate. I do still have to account for the pressure drop by including this P term here, and then also, since I have a non-isothermal reactor, all of these have this T naught divided by T term on them. So if this were a PFR with no pressure drop, I wouldn't need to include this term, and if this were an isothermal case, I wouldn't need to include this term. But that in this example, I have both pressure drop and temperature change. So we need to now get used to including these temperature terms on our concentration equations. The other thing I need to do is account for the fact that my rate constant and my equilibrium constant are no longer constants. They, in fact, vary with temperature. So I'm going to use the Arrhenius equations to scale those terms according to the temperature. To do that, I take the value at the reference, and then I do an exponential. To enter in the exponential, I'm using this math.exponential. Basically what that's saying is it's pulling this exponential function out of the math library. We've imported that, but this is the syntax to enter that in. In the case of the rate constant, I'm going to scale the exponential by the activation energy divided by the gas constant times 1 divided by the reference temperature minus 1 divided by the reactor temperature. And in the case of the equilibrium constant, that scale factor is going to be the heat of a reaction divided by the gas constant. I should also note that the gas constant, we're using the gas constant that has energy units. So the numerator in the units is energy. It's not volume times pressure. So I want to, again, to be consistent units, I need to pick a gas constant that has energy units there. Okay, so now I'm writing up my rate law. This is a reversible rate law. So I can write that out here, and then now I have all the information I need to write my system of design equations, my mole balance, my Ergun equation. Note here that the Ergun equation, I have to include this temperature dependent term, so that we haven't been including that in the isothermal case, but in the non-isothermal case, I have to include that. This is my energy balance, dT dW. That tells me how the temperature of my reactor fluid is going to change as a function of W. This I'm basically just copying down out of the notes with some exceptions. So I have this heat transfer coefficient here. I have to divide that by the catalyst density in order to get that in the correct units. So UA is in volume units, so I divide that by catalyst density. That puts it in mass units, which is then consistent with the other expressions in this system of equations. The bottom, the denominator here, so we have sum of I should have a sum of Fi times Cpi, so the flow rates of the different species times their heat capacities. In this case, we've said all of the heat capacities are the same, at least all of those for the reactor contents. So that in that case, I just need to multiply that heat capacity by the total molar flow rate. The total molar flow rate is equal to the inlet molar flow rates. The reason for that is since the number of moles or the molar flow rate does not change over the course of the reaction, that means that at any point it's always going to be that entering. So Fa naught plus Fb naught plus the flow rate of this inert. The inert flow rate, the inert never reacts, so the inert flow rate doesn't change anyways. But even if I even though the flow rates of A and B are changing, the total molar flow rate doesn't change. So the total molar flow rate is equal to that at the initial condition. So I wrote that down there just to simplify this balance. Initial conditions, so these have to be in the same order as up here. So my initial conversion is 0, my initial pressure ratio is 1, and then my initial temperature is equal to T0, which is a given value up here. Okay, so now this is the code to solve the ODE, so we can do that. When I do that, so we need to plot X, XE, T, TA, and RA versus the catalyst weight W. So I am going to rewrite some of these functions in order to do that. X is basically going to be, X, P, and T are things that I solve for, so those are the values coming out of Z here. So I just need to assign those to those vectors. I'm supposed to plot TA, but in this case it's constant, so I'm just taking the value that I'm given and I'm multiplying that by a vector of 1s that has the same length as W. So I'm going to plot TA versus W. So I want the same number of elements in W as are in TA, and to do that I can use this 1's code. Concentration equations, so these I'm just copying from above. Now what I need to do is solve for my rate constant, my equilibrium constant, my reaction rate, and my equilibrium conversion at each individual point. So a linear expression such as these, I can just write CA is a linear function of X, P, and T, so I can just write that out, and that gives me a vector of values of CA, and it basically takes each element in X, P, and T one by one, and it throws it into this equation, and then that's how it results in CA. The code will not do that when I have exponentials, so I actually have to populate this vector piece by piece. To do that, I am going to first predefine that these vectors, I'm going to assign them, every element is equal to 0, and again I'm going to say that they have length equal to that of W because I want to plot one by one. So that's just what this code is doing here. And then this code here says over each value I'm going to loop over and solve for something. So that's what I'm doing here. Notice now that I'm looping over the index J, so when I look at all of these different values, I have a J there, so I'm doing KJ and TJ here. But basically what this is doing is for every value of J, so J is going to go from 0 all the way up to the length of W, which I believe is 50 elements it ends up being. So it's going to go 0, 1, 2, 3, 4, 5, 6, 7, yada, yada, yada. And then each time it does that, it's going to create a value for K at that index position based on the temperature and the temperature vector at that index position, and so on and so forth for the equilibrium constant and the reaction rate. From there, I can use that information to calculate the equilibrium conversion. Now to do that, I could write that out algebraically, so I know what the reaction rate is, I know that equilibrium, the reaction rate is equal to 0, and I know the equilibrium constant, and I have values or expressions for the different concentrations as a function of conversion. So I could manipulate that algebraic expression and come up with an algebraic expression for the equilibrium conversion. There is just too much complexity there, given that there's squares in there, and there's temperature changing in there, and there is pressure drop terms in there, that I do not trust myself to do that algebra without making any mistakes. So instead, I'm going to set this up as an equation, and I'm basically going to use this fsolve function. What fsolve does is it finds the roots of that equation. In this case, it's going to find the value of x that sets the reaction rate equal to 0. So again, this is within my for loop, so as I loop over values, I'm going to find the equilibrium conversion at each case. So that's what I'm setting up here. In this case, I don't know what x is. I'm going to solve for that, so I give it just a dummy variable, but then I relate, and in fact, here what I'm doing too, I'm not using Ca. I want to know the Ca of equilibrium, which may or may not be the same as the actual concentration. So I want to find the conversion that will result in that equilibrium concentration, but I do take the pressure and temperature at that particular condition. And I do that for A, B, and C. That allows me to write the expression for my rate. Normally this would have K written outside, but since we can divide both sides by K and we'd still get 0 on the left-hand side, I just really need to know when this term is equal to 0. That tells me that I'm at equilibrium based on the value of my equilibrium constant. So I'm going to do that for each value of my equilibrium constant along my vector, and I'm going to get an associated value of xe, and then I'm going to use that to populate this xe vector. So that's what all of this code in here is doing. Now I can plot the different results. I'm going to plot my x's on one graph, my temperatures on another, and my rate on another. And on my x graph, because it's the same order of magnitude, I'm going to plot p also. I know I wasn't asked to do that, but it's helpful for me to see how p is behaving, just so that I can understand the system a little more. So these are the graphs that I get. So you see for x, the conversion increases until it essentially meets the equilibrium conversion, which is this black line, and those follow each other for a while, although at some point x is a little bit ineffective as it's not able to fully achieve the equilibrium conversion. In a reversible reaction, the maximum conversion possible is the equilibrium conversion, so what we want is for the reactor to achieve that level of conversion. Here's my temperatures. So we see the temperature of the reactant fluid starts out a little bit higher than that of the cooling fluid. The reaction at first proceeds pretty rapidly because it's far away from equilibrium. As it does that, the temperature increases, given that it's an exothermic reaction, until eventually it hits a point where the equilibrium constant is going to really start favoring the reverse reaction. In that case, we see a dramatic change in the rate, drop off of the rate, and because of that, we also see the temperature decreasing. So that's what's going on in these two graphs. Okay, so the second case is the adiabatic case. In this case, we're basically going to make a modification to our energy balance equation, so we remove the heat exchanger term, so there is no UA delta T term in the adiabatic case. So if you look at the mole balance and the energy balance here, those actually are related to each other. They're actually linear. One is a linear function of the other. So both have RA, both have FA naught. So in fact, I could take this denominator in the energy balance and I could convert this into FA naught times a sum of the heat capacities. And it would give me the identical values as I have here. So then really the TdW is equal to the XdW times negative heat of reaction divided by the sum of the heat capacities. So all of the heat capacities added up together. So what that tells us is that alternatively, I don't need to write a differential equation here. And in fact, if you look at chapter 11 in the book, you can find a linear expression between x and t for adiabatic reactors. And so that expression doesn't depend on which reactor you're using. You can use it for a PFR, you can use it for a CSTR. That's because energy is a state function, so it doesn't matter how you get from one point to the other, or the path doesn't matter how you get from one point to the other, as long as the point you arrive at is the same for the different reactors. So when we remove heat exchange, that's really the only thing influencing the relationship between conversion and temperature for the different reactors, is how that heat is transferred. In fact, the area over which it's transferred. So because of that, we could write the energy balance as a linear function. We don't need to use a differential equation. That said, if you're already using Python and you already got it set up, it's pretty easy just to delete the the heat exchanger term. So that's what I did here. Of course, there are multiple ways to solve every problem. One way that you could do that is to treat the energy balance for an adiabatic system as a linear function of conversion. So just keep that in mind. Everything else here is the same as in the last case. Yeah, so then I can go ahead and look at my different graphs. You see in this case, because I have adiabatic, the issue becomes that I quickly rise up to this temperature, this 400 degrees, where my reaction just starts going in reverse, or the equilibrium constant favors the reverse reaction. Because of that, the rate goes to 0, and when the rate goes to 0, that means x is no longer progressing, which means t is no longer progressing. So basically, I have an initial spike. So since there's no coolant, the temperature rises, the reaction rate starts increasing dramatically, and the reaction rate spikes, but then the reverse reaction comes into play and stops the reaction, essentially. So the heat exchanger is actually doing a service in this regard by helping to get a little bit higher conversion by keeping the reactor contents below this 400 degrees. Whereas in the adiabatic case, we quickly achieve this 400 degrees and then the reaction stops. That's what you see here. The conversion quickly goes to the equilibrium conversion and then just stops. Okay. So now we'll look at the co-current heat exchanger case. In this case, now I have to have when I set up my system of ordinary differential equations, I need to include TA. So TA is a variable, and we're going to have a differential equation for it. That's the major change coming from the last two examples to this one. So one thing I have to do is say that TA is variable, and I do that by defining it as its values are going to be part of this Z3 matrix. The other thing I have to do is set up a differential equation for TA, for my cooling fluid. So we said in the last lecture that this is going to look a lot like the heat exchanger part of the dTdW term. So that's essentially what we have here, except that we switch the order of the temperatures in the parentheses in order to make sure that the heat is transferring appropriately. So heat transferring to the system should increase the temperature, whereas heat transferred away from the system should decrease the temperature. So given that the system is, in this case, the reactor fluid and the surroundings are the coolant, whereas here the system is the coolant and the surroundings are the reactor fluid, we switch these in this parentheses. Other than that, everything is pretty much the same. I need to include this here now in my system of ODEs, so I do that. And then additionally, when I set my initial conditions, I need to set an initial value for my coolant temperature. When I come down and solve the problem, then another thing I have to do is, if I want to plot TA, then I have to assign it to these values that were solved for. And then when I write any of equations in here, actually none of the equations in here rely on TA, so I don't need to worry about it there. All right, co-current. So again, here are my plots. So my plots for X. So again, my rate increases pretty rapidly. I get up to this about 400 degrees. That's where my reverse reaction comes into play. But now I have a heat exchanger again. So the heat exchanger works to reduce the temperature, and because of that, the temperature, the conversion is allowed to keep increasing over the course of the reactor, albeit somewhat gradually. So you see here the equilibrium conversion meets with the actual conversion, and then they track each other for the remainder of the reactor. You also notice here how this reaction quickly, so one way we can explain this is this reaction is becoming equilibrium limited. We ultimately would get to a temperature where we couldn't get any more conversion because the reaction is starting to go in reverse. It's starting to it's gone into equilibrium. So, and what would be nicer if we didn't have to overcome a kinetic barrier, maybe we could more quickly follow this equilibrium conversion, and in this region we could almost get up to 1, but we can't. So here we're limited by kinetics. So this is actually a pretty significant issue in reactor design and also catalysis. A goal of catalysis would be to define a catalyst that has a lower activation barrier, which means that we can get to a higher conversion sooner. And in fact, this being a catalytic reactor already, that would mean we would want to find a more effective catalyst where we don't have this kinetic limitation here, which is preventing us from achieving the equilibrium conversion, which at these temperatures is quite high. Instead, we have to heat the reactor contents up pretty significantly in order to get in order to achieve the equilibrium conversion. By the time we do that, though, we've achieved a temperature where the reaction likes to go in reverse. So this shows you the importance of designing catalysts that have low activation barriers. Okay, so in the final case is our countercurrent case. I said all of this is the same except I make the differential equation for the cooling fluid. I basically turn that into the negative of the co-current case, and I do that because I'm switching the limits of integration. So not because I want heat to transfer in a way that's unphysical, but I need to switch the limits of integration. That's how I do that. In this case, we also said that we only know the temperature of the cooling fluid when V equals V, or in this case when W equals W, which the way I've set W would be 5,000. So I know what W is at a catalyst weight of 5,000 kilograms. That's this 300, right? This TA naught, this one. So I know that value. What I don't know is what the temperature of the cooling fluid equals at V equals 0, because that's the outlet temperature in the countercurrent case. So I have to determine that. You might as well consider that to be an additional unknown with an additional equation. I know what the final temperature of I know what the temperature of TA at the final catalyst weight is, but I don't know it when the catalyst at the reactor inlet, where catalyst weight is equal to 0. So I need to do guess and check. So to do that, I'm going to start. So I already know the answer because I've already worked this problem. But my first guess, is going to be about 400. So if I go back here and look at my co-current case, I say, okay, the temperature of the cooling fluid is increasing, maybe somewhere between, the exit temp in this case would be somewhere between 360 and 380. So anywhere around there is fine. I just kind of almost arbitrarily chose 400, and then I can pick, and then I can just solve for that. So one thing I've done here is said to print. I want to print the final value of my, I want to print the final value of the temperature of the cooling fluid. So that means the value at W is equal to 0. So I'm printing that, and then I can go look at what that is here. And if I start with this value, an initial guess of 400, then the value at W equals 0 is equal to 620, which of course is much too high. So that tells me, okay, let's decrease. So, maybe I decrease to 350. So I decrease to 350, and now my exit is minus 100. So that's not even possible, given that we are working in kelvins. I can't even, minus 100 is not even it doesn't even exist in the known universe. So now I need to change that again. So let's hit the middle here. So 375. I go to 375. Now I'm getting closer. I'm at like 215, still too cold. So let's just gradually bump it up. And in fact, I know what the answer is. So let's say 380. When I say that the outlet temperature is 380, so that would be the temperature at W equals to 0. Then the inlet temperature at W equals to 5,000 is equal to this 300, or approximately there, right? So I'm not going to worry about this 0.6722, blah, blah, blah. So that's how we do that. We basically do guess and check until we get the value or the inlet temperature, which is at the outlet position for the remaining ODEs. We do that until we get a value that was specified to us. So when that cooling fluid enters the product side of the reactor, we know it's at 300 degrees. So that means that when I solve the problem, the final value at, which is the one at W is equal to W, better be 300. So what initial value, which is really the final value, but it's at the initial position, what value gives me this correct answer? So it's basically, like I said, a guess and check solution. The only other difference here to remember is that because we're switching these limits integration, you got to put a negative sign here or switch the positions of TA and T in the parentheses. Okay, so go down here and look at the rest of the answers. So they look, at least the conversion graph looks a lot like in the co-current case. We had a little bit less time or a little bit less catalyst weight to achieve the equilibrium conversion, but we do achieve it pretty rapidly, and then we track the equilibrium conversion and for the remainder of the catalyst weight. We also achieve 400 degrees pretty rapidly. This is because by the time the cooling fluid gets to this point, by the time it's exiting, it's become pretty hot because it's been cooling the reactor over the course of 5,000 kilograms of catalyst already. So its temperature has risen pretty dramatically. So it pretty ineffectively cools here at the beginning. The greater cooling is done here at the end. Due to the fact that you're getting a fresh coolant in. But that's, I think, a difference. I think we're taught, we think about heat exchange when we first learn about it, we learn that countercurrent is more effective. Here's a case where when you have a chemical reaction, that's not always true because the chemical reaction is releasing so much heat that it's heating the cooling fluid significantly. So really, if you compare the countercurrent and the co-current heat exchangers in this case, they're operating pretty similarly. So here's just some summary that's been printed out. So final conversion for each case. The constant TA case gives the best conversion. It keeps the temperature low enough. It most effectively keeps the temperature low enough to prevent the reversible reaction from coming into play. The heat exchangers are next. They give pretty similar conversions, and then the adiabatic case is the worst because it very quickly goes up to about 400 K, which is where the reaction comes into equilibrium, and then the rate stops. So that's what's also being said here. When the temperature gets to about 400 K, the reaction comes into equilibrium and the rate goes to 0. The heat exchangers keep the temperature below this value so that the rate is finite. The constant TA case does the best job at this. The adiabatic case does the worst job. In this example, the co-current and countercurrent heat exchangers act similarly. Both keep the temperature below 400 K and allow the conversion to track the equilibrium conversion. This despite operating differently, which can be observed from the T versus TA trends for both graphs. So if you look at this graph versus this one, they look a lot different. So a lot of different things going on, but when it all comes down to it, they're operating pretty similarly. Notice how the countercurrent heat exchanger immediately heats up the reactor fluid since it is so hot at the exit. So in the countercurrent case, the TA is actually transferring heat to the reactor fluid at this point because it's become so hot due to exchanging heat with the reactor fluid over the course of the catalyst weight. So that is what I want to show for this example. Hopefully this serves as a good template for you.